Hello, my name is Mo Kim. I'm an assistant professor with Department of Electrical and Computer Engineering at Georgia Southern University in the United States. This talk is about my paper entitled Reinforcement Learning for Accident Risk Adaptive V2X Networking. Vehicle to everything, or V2X communications, have the potential to significantly bring down the number of vehicle crashes, thereby reducing the number of associated fatalities. The capability gave V2X communications the central role in constitution of Intelligent Transportation System, or ITS, for connected and autonomous vehicles, or CAVs. Due to the very high mobility of vehicles, there will be frequent change in the topology of the network. Mainly, routing and security are affected by this frequent topology change. In practice, many environmental factors such as traffic amount or pattern and traffic regulations influence the risk level to which a vehicle is exposed in real time. Nonetheless, the existing V2X communication schemes cannot reflect dynamic traffic patterns and environmental changes. In a CAV environment, the vehicles must be able to explore, learn from, make accurate evaluation of the level of an accident risk, and adapt their transmission of basic safety messages to the environment. To date, there's no proposal fostering such a capability at each vehicle. This makes a compelling case that a V2X network should employ a machine learning functionality to keep itself nimble on the fly without the need for external updates, which causes additional delay. The approach that this paper takes toward achieving the purpose is twofold. First, we propose to allocate the network resource based on the accident risk that each vehicle marks. Specifically, we propose to prioritize a vehicle marking a higher accident risk in granting a channel access. Second, in order to make each vehicle update the environmental information on the fly, we propose to employ online machine learning, which is known to be efficient when the data has to be learned partially over time. Here we summarize the contributions of this paper. Firstly, our proposed learning framework is extendable to other types of input defining the environment of a vehicle. Secondly, the method of our defining an accident risk is also general. There are too many factors defining the risk of a vehicle. Henceforth, the proposed accident risk measurement model aimed at generality, so it can be extended to any other factors. Thirdly, the proposed mechanism is designed to run on each vehicle autonomously without any aid from a central entity for any external updates or prior knowledge. We define the system model of this paper on two different fronts. The first of the two is the perspective of networking. We assume a distributed network where no central coordinator or infrastructure exists. We leave it as a general distributed network type, which can be implemented in the form of DSRC or CV2X Mode 4. We also assume periodic broadcast of basic safety messages. Furthermore, all the nodes are supposed to be fully connected. The second component of the system model is the geometry. We assume a general two-dimensional space with no lane separation. So it can be applied to any scenario, such as vehicle being able to move in any direction, and the nodes are distributed following a homogeneous Poisson point process. Notice that we model the proposed multiple axis mechanism as a multi-armed bandit problem, where each vehicle becomes a bandit and makes selection of an action or arm depending on the context that it experiences. As the figure displays, in each time slot, a bandit, in other words, a vehicle, makes a selection among arms accounting the context that has been observed in that time slot. Each arm selection leads to quantification of an accident risk level, back-off counter, successful transmission or packet exploration, and a reward. The vehicle learns from the rewards collected in the arms to make the choice of an arm in the current iteration. Over time, the vehicle's aim is to collect enough information about how the context and arms are mapped to each other, so it can predict the next best arm to play by looking at the incoming context. In each discrete time slot t, the bandit, in other words, an arbitrary vehicle in the network, performs the proposed algorithm to learn the context in the changing environment and be given an opportunity to transmitting a basic safety message in accordance with the results of the learning. A detailed procedure follows as below in this algorithm. The bandit is given a certain length of training phase at the beginning. In a training phase, upon observation of a certain context, an arm is chosen uniformly randomly among the arms. The weight for the context selected via the selected arm is used to compute a value for accident risk, or AR. We performed numerical calculations for evaluation of the performance of this proposed mechanism, and here are the parameters and their values summarized. These two figures provide heat maps to demonstrate how the reward is distributed versus the context and arm. They compare different representative multi-arm bandit strategies, namely A/B testing, which is uniform random, and epsilon greedy. One can observe from the comparison between these two figures that a higher probability of exploitation, which is 0 here and 0.9 here, yields a clearer outperformance of the following the optimal strategy. While an A/B test, blue lines, remains to be random all the way through observation time, an epsilon greedy strategy, which is expressed in the red line, explores only at a given probability for this length of time. The epsilon greedy strategy is not able to find a completely accurate arm as the optimal strategy does, heavily due to a short training phase and discretization in the categorization of each context into the arm separation. The regret that's expressed here is approximated to be around 0.15 in the example shown in this figure. Now we present how the performance of a V2X network is improved after applying the proposed mechanism. Notice that the vertical axis indicates the probability of transmission after making through a back-off process in IEEE 802.11p CSMA-CA multiple axis. What the result shows is that the proposed algorithm grants a higher chance of transmission to a vehicle with a higher accident risk. So, to conclude this presentation, the key proposition of this paper has been twofold. First, a reinforcement learning framework enabling a vehicle to autonomously adapt itself to dynamic environments. Second, a V2X networking protocol prioritizing a vehicle with a higher accident risk. This paper formulated the reinforcement learning framework as a contextual multi-armed bandit problem where the multiple arms are used to test all possible values for the weight of a certain context. The proposed mechanism yielded that each vehicle's axis was allocated based on the accident risk, and therefore we were able to get a higher performance, which is the transmission probability after making through a multiple axis protocol after applying our proposed mechanism. So, well, this concludes my presentation. I appreciate your listening to it. I hope you enjoy the rest of this conference. Thank you very much.